Hi, I'm Steffen Grunwald. I'm Solutions Architect at Amazon Web Services, and part of my job is to help customers to optimize their workloads in regards to security and reliability and operations, and also performance and cost. And if you're watching this session now, it's probably because you love Java or you love AWS Lambda. And I have good news for you. In the next 30 minutes, I want to show you some tricks which you can apply to your Java applications running on Lambda to reduce your effort and cost while increasing performance. And some of these tricks will be applicable to Java in general, also in containers or on Amazon EC2. And there will be other tricks which you can also apply to other runtimes running on AWS Lambda. Let's start by talking about the elephant in the room. Java, that old language that just turned 25, why should you even bother? And the reason is there's lots of talent out there, but also there's a rich ecosystem of tools you can use to develop efficient Java applications, and also a wealth of libraries which you can draw from for your application code. If you look at the lines of code of the Apache Software Foundation, you see that at any given point in time, almost half of the code was written in Java. Only recently, all programming languages experience a dip in favor of JSON. Maybe that's because Java code is now migrated to JSON. Just kidding. So why should you even optimize? Let's think about optimizing one aspect, and that is performance. If you look at the Lambda pricing, you are billed by the amount of requests, and also by the execution time of memory provisioned measured in 1 millisecond steps. This has recently been changed. Previously it was by 100 milliseconds and also with a minimum execution time, but now there isn't even an execution time, a minimum execution time. So that means if you take just one of those tricks I will show you later and apply it to your code, and you shave off maybe 5% of the execution duration, that will not only make your customers happier by using snappier application, but also you will get the same reduction automatically in your Lambda bill. So at the beginning of every optimization session there should be this disclaimer, and that is, there is no silver bullet. Every application is different, and if you take those tricks that might turn out useful for you and might have a good effect, but to be honest, it also can have a negative effect on your processes or on the overall runtime of your application. So always measure, then optimize, then measure again, and repeat this cycle. What we are going to look at is the whole life cycle. So we look at build, deploy and run, and then monitor. But as monitoring and measurement is this important, as I just said, we will look at this first. And that is about watching or observing what's done inside of your Lambda function. And there's a lot of things going on when an event hits Lambda, but let's boil this for a moment down to just 3 simple phases. And that is, first, an event hits Lambda. Lambda downloads your code and starts an execution context for the execution. Within this execution context, the JVM is started, and also your handler classes are loaded. And in the third phase, your handler class is used, and the method is called, your handler method is called with the incoming event, and it's executed. AWS X-Ray is a service that records all these phases as segments, stores it, and also visualizes it in the console, as you can see here. All you need to do is activate tracing in the Lambda console, or you can also do this via CloudFormation template or via the API. And then you have a good outsider view of what's going on in these phases and how much time they take. To look what's going on inside of your function, you can also use the X-Ray API to emit custom segments and to see and visualize certain parts of your code. One common way to look inside of your application is logging. And at the start of every execution context, Lambda also creates a log stream inside of Amazon CloudWatch logs. And every line you send and you write to standard out and standard error is also put to this log stream and visible in the CloudWatch logs console. So this is something which you can use to easily debug and log. You can also use the Lambda logger, which is an object you can retrieve from the context a parameter passed to your handler. And there you can also use multi-line logging to get many lines in one single CloudWatch logs message. One common way to log in the Java world is using log4j, because you can define different log levels like debug and error, and you can define those different levels on for very fine-grained for your classes or for certain packages to see to turn on and turn off your logs. One other method or one other benefit from log4j is that you can decorate your log messages with useful context, like the timestamp and also the thread name, for example. But please refrain from using the caller information patterns like C, M, and L. This is a very convenient way to log the class name and the method name where you're logging, and also the line number. But think for a moment about how log4j does get this information at runtime. It does so by creating a stack trace and parsing that stack trace. And this, you can imagine, is quite an expensive operation at runtime if you log often. Let's look at build and development and look at maybe most of the most simple functions you can implement as a handler. And this here is just a handle request method that takes an event as here in string format, and also the context object as passed by Lambda. One of the reasons you're using Java is probably because of the type safety. And this type safety you can get by, for example, by taking the request handler interface from the AWS Lambda Java core library, which is available on Maven Central. Implement that so you make sure you have the right method name, and you also can define the input-output objects. And furthermore, here in this case, I'm using an input event that is of type string. I've seen at customers having strings with JSON objects, and they are parsing that string in their code to create objects from that. You can do this, of course, but it bloats your code a bit, and you also need some dependencies to do this parsing. What you can do instead is to use the built-in data binding that comes with Lambda. Lambda takes your JSON code automatically and unmarshals a Java bean from that of your choice. So you don't have to do that in your code. And you don't even need to define that Java bean yourself, since common integrations like S3 and API gateway events are already provided as pre-canned beans in the AWS Lambda Java events library, which is also available on Maven Central. Let's go on to the deployment. And here your code will probably always use some libraries because you don't want to implement everything yourself. And you can use these libraries and package those. And there are two options which you can choose. Here I'm showing the ways how you create this with Maven, but you can also use other build systems to do the same. Option A is you're creating a single flat jar that contains, of course, your application classes and also contains all classes from your dependencies. So all copied flat into the same jar. Option B is that you create a zip file that also contains your application classes but has one lib folder, and inside of this lib folder in the zip there are the jar files directly put. Both have their benefits. I'm listing a few here. So this option A, that flat single jar, is obviously also loadable and understandable for a class loader that does not know about the lib semantics. Option B will most likely result in smaller package sizes, and it for sure the package phase, the building of the zip file, is faster since you don't need to unzip and zip the dependencies again. But the best benefit here is that you can easily track and inspect why your zip is so big. So you can go to the zip and look at the dependencies and the transitive dependencies, and maybe one of them sneaked in, so you can easily find out why this zip has become so big since the last build. Let's come to the maybe most interesting part, and that is the optimization of the runtime of your application. And here I want to take you on a journey and start that journey with a sample application. And I will continuously optimize that sample application in the next steps and show you the results of that. So the sample application I've picked is from the Lambda docs. There is code which is consuming, or is example code for consuming S3 events. And this code has been written with comprehensiveness in mind. So you can imagine that you can apply some additional tuning, and also by making some trade-offs you can easily make this function faster. This function starts with a upload of an image into S3. S3 triggers the Lambda application and sends a bucket name and an object key. Lambda is taking that bucket name, object key, downloads the object, the image, then resizes the image, and afterwards puts the result back to a different bucket. And I'm using a 10 kilobyte image file here because I want to reduce the effect of the image size of the data transfer to the function execution duration. And I defined the function memory with 512 megabytes of memory. What does it mean? Yeah, it obviously means half a gigabyte of memory, but also it has an effect on the allocation of other resources to your Lambda function. Lambda defines or allocates CPU and network resources, for example, also proportionally to this setting. And this can speed up my function significantly. So although it is more expensive if I provide more memory, it's more expensive per millisecond, also my function will execute faster and the build duration will also be shorter. So overall it is an improvement, or it can be an improvement. It is the easiest tweak that you can do, and it's also one you should start with. But what is a good setting for your individual application? This question is answered by the Lambda Power Tuning tool. It's an application written by a colleague of mine, and it's also available in the serverless application repository. And what it does is it executes your function with different memory configurations, and it tracks the execution duration for each configuration and indicates what was the best configuration regarding the execution time and what was the best configuration regarding the cost. And you can see here with this blue line, the cost is almost independent of the memory provisioned. On the other hand, the execution duration, this goes down and is significantly less with 2 GB of memory. So this would be a good setting which you should pick for this application to experiment with. And the memory setting also has an effect of your abilities to use multithreading. So you can use multithreading. In my case, it's not so helpful because I need to download and resize and upload the image all in sequence. But if your application is I/O bound and you need to, for example, download many images at once for resizing, then you could benefit from multithreading here. If your application is CPU bound, you have to consider if your application even has access to multiple CPU hyperthreads. And that is the case starting from about 1.8 GB of memory. And there you will probably see some gains from using multithreading. I wanted to go deeper into the lifecycle of the Lambda function and look at the 3 different phases. One is build and deploy, where you or your application, your build server is taking the code, compiling it and creating a package and putting that package to Lambda and creating a function, deploying a function. The second step, the second phase I want to look at runtime is when an event hits Lambda for your function, then Lambda creates an execution context, it downloads your code, it starts the JVM, and it also starts and loads your handler from the downloaded code. And in a third step at runtime, then your handler is invoked with the event which came in. And there are 2 types of starts for this execution at runtime. You typically see the initialization of this initialization part. You see it when your code has when your function has just been created, or it has been updated, or Lambda is creating or is scaling out execution contexts in anticipation of more incoming events. And this is called a cold start. Afterwards, after the invocation of the function has finished, Lambda freezes the execution context and waits for other events coming in. It thaws the execution context when a new event is coming in if Lambda chooses to reuse that execution context. And this is called a warm start. A warm start does not involve the execution of the initialization phase of the parts there. And for the further measurement, I measured the average of both of 4 warm starts and 4 cold starts. There's one thing special about these lifecycle phases, and also something which is very important for the upcoming optimizations, and that is up to the point where Lambda has created my handler class. I have access to more host CPU than I have during the invocation of my handler, and that is up to 10 seconds. Now we can use this information and do things which are usually done at runtime by the handler, and do these ahead of time. During the build and deployment, where I have all the time in the world to pre-compile things, to generate code, and so on. And B, in the initialization, in the first 10 seconds of this phase. But be careful, don't do too much in the initialization phase. Don't exceed that 10 seconds, since if you exceed it, it will affect the way the whole initialization is built. It will be built then at the pricing as indicated in the Lambda pricing, without any initialization specific discounts. Now I can take this strategy and move these blocks from right to left at one by one. And let's start with clients. Your code will probably not be standalone, your application, but call some backends on-prem, in AWS, and also AWS services. And to call something, you need to load the classes for the client, you need to discover endpoint addresses and host names, and also you need to configure the client. And ideally, you do this only once. It turns out that the sample code is doing this at every invocation of the handler. And I just used this block and put it to the constructor, and I can also put it to a static initializer. And then it is done only once at the initialization. The result is that the initialization takes longer, but on the other hand, all handler invocation in the cold start and in the warm start is taking much less. So I reduce the cold start from 14 seconds to just 8 seconds. And we could go further. So think about when a client is created, it discovers some configuration, it parses some metadata and discovers the configuration it's deployed to, the region it's deployed to. And if I know already at build time that I will deploy my classes to deploy my application to Frankfurt, I can already hard code the DNS name of my endpoint if I want. Talking about the client, I can also use for calling AWS service the AWS SDK for Java 2. That does give me some benefits if I want to execute things in parallel due to the non-blocking I/O feature. Here I'm using the pluggable HTTP client feature and change the HTTP client to the common runtime async client to do the S3 operations. And this cuts again the execution time of the cold start from the 8 seconds to 5 seconds. Let's look at one thing every application does, and that is reflection and class loading. You should look at your code and inspect your code for expensive operations. Lots of classes loaded by a library, or lots of reflection being done, or parsing metadata. This is something which you ideally already do in the initialization phase. Or you just do a very blunt approach, as I did here, by calling the whole handler from the constructor once with dummy data. So here I'm using a very small image. I'm calling the handler. It does all the client creation. It even does the backend calls to S3. And this, of course, has an effect of the initialization phase taking much longer. But on the other hand, the cold start has much less handler time here. So I cut it basically the whole cold start in half by that. So I moved reflection now to the initialization phase, and let's look now at dependency injection. Your Java application on Lambda will probably not be the next monolith. So you have a few classes, maybe 5, maybe a dozen of those. The question is, do you really need dependency injection to wire this all together? My recommendation would be don't. Because you need some dependency injection libraries also to do the dependency injection. And also, if you rely on the very convenient way to discover your classes and discover your beans by annotation scanning, then this adds additional class loading, which is expensive. There are cases where you use dependency injection, for example, for lift and shift migration. So if you have an application, you want to move it to Lambda, maybe you don't want to start with refactoring, and this is a valid approach. If you do so, please take a look at the AWS Serverless Java Container project, which provides means to create this application context easily in the constructor or in static initializers. And it also has some mediation between common events coming from S3, for example, or API gateway, and mediating those two the interfaces that are common to your framework. If you want to use dependency injection by all means, then please take a look at dependency injection frameworks which do the discovery and this wiring at compile time, where you have more time to do those things. Dagger is a framework which is popular for doing that. Let's look at one thing every application does, or every Java application does, and that is the heap management, the heap resizing. What is the size of the heap of your Lambda function? Do you know? You can monitor this, and I also monitored that for my application and looked at 100 consecutive calls to the same execution context. And what you can see here is that the heap starts with almost 0, and then as it is called ramps up to a certain heap size, and it continues to be resized then afterwards. You can experiment with a fixed setting of the heap size to reduce the time that is spent for the garbage collector, and you can also define that heap size according to your function's needs. Think about my application. I'm downloading an image, then resizing it, and then uploading it to S3, and I only need that image to be around in the heap for this very resizing. So it makes sense to pick a heap size that allows me to only keep to not upload or use the tenured space for storing the image, but making it possible for the garbage collector to collect the whole image data in a minor garbage collection to reduce the effort spent for garbage collection. There's one block left, and that is just-in-time compilation. When your Java application is executed, the JVM continuously creates statistics about the execution of the functions of the code. And the just-in-time compiler compiles the code methods that are called often to platform-specific code. And it also does some other optimizations like inlining small functions and so on. On the short term, this is a very expensive operation, but on the long term you will see that the function executions converge to a relatively short duration after just tens of executions. The GraalVM project provides means to create a native image from your code at compile time. And the resulting program has faster startup times and also less memory overhead. It does so by, GraalVM does so by statically analyzing your code. So it only does know the information about your code, and can only use the information it can get from your code and from your dependencies. And this has some impact on how I need to write my code. For example, to use reflection or to use native code. And it might also be that some applications are not a good fit for GraalVM, so are not a candidate for being compiled by GraalVM. If you use frameworks like Quarkus or Micronaut, these are integrating with GraalVM well because they are supporting that in their build process. And they also have these limitations in mind when for example, calling AWS services. As it happens, this Java application I have here is not a good candidate for being compiled with GraalVM, since that resizing is done with AWT native code, and that needs special care and also maybe a replacement. But just to show you the effectiveness of using GraalVM, here's a sample application that also does some backend calls in DynamoDB in this case for create, read, update, delete. And what you can see on this log scale is that, on that log scale graph, is that the benefits are almost 95% of the cold start and the warm start. So this is a very efficient effective operation if you can use GraalVM and your application is the candidate for that. So even without GraalVM and without the power tuning, now I've shown you some improvements which are adding up to 71% of the cold start and 80% of the warm start. And you might now wonder where you should start with your application. What should you do first? And I took the results and the experience from this experiment with the sample application and put it to this map and aligned it on the map to the easiness of the optimizations and also the effectiveness of the optimizations. And you should of course start on the top right with the quick wins. One thing which is very important is you start with monitoring. That does not change much, of course, of the of your execution duration, but you easily see where's the time spent, which is the function I should tune first, and was this measurement even effective? And you should try also the other optimizations in this map here. And I want to leave you here with this map and thank you for attending this session. I'm curious to hear your success stories, so the effectiveness of these optimizations, or maybe you have own ones which were proven to be helpful in your application. So eager to hear that. Feel free to reach out to me on Twitter and send me a message. One last ask, please complete the session survey for this session. Have a nice day. Thank you. Bye-bye.